So now we've demonstrated how you do basic machine learning with Flux, but we want to do deep learning, that is, getting to lots of neurons stacked together in many layers. And one of the core features in doing that is having multiple outputs. So in this notebook, we'll look at just one neuron with many outputs and see how that works. So that way we can begin building up to have bigger and deeper networks. So let's extend the example from the previous lecture where we were discriminating between apples and bananas and throw grapes into the mix. Whereas before we just had one output with zeros representing apples and ones representing bananas. That doesn't extend very well once we start talking about grapes or avocados or more fruit. Because if we were to give a grape a value of 2, then that kind of implicitly is giving some extra meaning to our data that's not there. A banana isn't grapier than an apple is, for example. So what we want to do is have multiple outputs where we actually have a vector of outputs. And we have 3 outputs in this case for the very simple reason that the first element is basically saying, is this an apple? So for the apple, yes. But for the banana and the grape, of course, no, they're not apples. The second element of our output vector is asking, is it a banana? So no, yes, no. And the third element of our output vector is asking, is it a grape? So in this manner, we can extend to arbitrarily many outputs and have them represent lots of different categories of things, not just 3 fruits, but hundreds of meanings of words or arbitrary categories. So that is a very important core technique of machine learning. So how would you represent this in a neural network? Well, one way to do that would be to have 3 separate neurons, right? Each with one output, each computing the question, is it an apple? The next one computing, is it a banana? And the last one computing, is it a grape? This is what those expressions might look like, right? It's just the sigmoid function with our weights for is it an apple times our input features plus a bias for that is it an apple neuron. Same thing for the is it a banana neuron. Same thing for the is it a grape neuron. Well, if you look at this, this is essentially a linear system of equations. This part here is the linear part hidden inside this nonlinearity. Well, this linear part is precisely what we can use to extend to a linear system of equations. And this is the core of linear algebra. If it's been a little while since your last linear algebra class, that's all right. Just bear with me here. Basically, you can represent the biases as a vector and the weights as a matrix, such that all of your weights are in rows. So that way the first row here is asking, is it an apple? The second row is asking, is it a banana? And the third row is asking, is it a grape? And now remember how Flux set up our neuron in the last example with just one output as a single row of our W matrix. Now you can see why that's so important and why that's a key feature, because it easily lends itself to extending to multiple outputs, where each new row in our weights matrix is essentially another computation, another hidden neuron in our model. So this can all be written as the big matrix multiplication now between W and X. And again, this matrix multiplication, it's not very complicated. It's essentially doing the dot product that we've been doing all along. And you can see that if we kind of cleverly set up our W's and X's, so that way you can see where everything comes from. So in my one column here, I have 10, 20, and 30. In the other column, I have 1, 2, 3. So now when I multiply W times X, you can see that the first element in the output here is 3 times 10 plus 2 times 1. The second element here is 3 times 20 plus 2 times 2 is 64, and so on and so forth. So you can tell that this is just going in, grabbing that first column, and doing the dot product against X. So here's that first element, second element, and so on and so forth. So that's matrix multiplication. What's kind of cool is that this actually extends to not just matrix vector products, but matrix-matrix products. So for example, I could add another column in my feature space, or my X vector here, and do the same product. And now you can see that the second column is populated by the dot product of this second column of the X's. So now, you know, each column is basically going through, and this is the 1, 2 element of our array here. So the second row, first column is populated by the dot product between the second row and the first column. So that is an extremely powerful technique. For now, we'll just use vector X's. But keep this in mind, the fact that you could potentially evaluate many features all at once, and you might be able to gain some efficiencies in doing so. This is called mini batching. So we're not going to cover that in this notebook, but keep that in mind. It's an important technique to improve the speed of your processing. So that's matrix multiplication. And now you can think of every single neuron in your system as a matrix multiplication, right? In the 2 input, 1 output version, we had a 1/2 matrix of weights W that we multiplied together with our input features and got a single output. But if we have a 2 input, 3 output, now we have a 3/2 matrix with 3 rows, 2 columns, and we multiply our 2 element vector by that, and we get 3 outputs now. And so this gives us a way of doing non-binary classification. It also hammers home the importance of that matrix multiplication. And this is why GPUs have suddenly become such an important part of machine learning, because GPUs can do matrix multiplications fast. It's something that you need to do a lot of graphics processing, and it's something where, you know, games came up with this first. They realized, oh, we need to do lots of matrix multiplications. And now we're realizing, hey, so do we data scientists as we're doing our machine learning tasks. So that is the power behind a graphics processing unit. And so each one of these layers is a matrix multiplication. Now you can also begin to imagine how the output from one of these neurons could actually just be tacked together as the input of the next neuron. We're not going to get to that yet in this lecture, but keep that in mind for the next one. So let's see how this works with Flux. First, we need to load the data. I'm not going to get too in depth with how this data loading works. It's just like the last lecture that we talked about. Basically, we're adding in some extra data files for apples, and now we have 2 data files for our grapes as well, and we're concatenating them all together. So what's being spit out here at the end is our data frame of all our grapes, and that looks just like what we were used to from the last lecture. Now we also want to extract out all our labels, and again we're going to look at the red and blue values from each data frame. So we have the red and blue of our apples, the red and blue of our bananas, and the red and blue of our grapes, and we concatenate them all together into our X's. But now for our Y's, what should go here, right? So how do we do this? Before we had fill a 1 the size of X apples, and fill, or I guess it was fill 0, sorry. Fill 0 the size of our apples, and fill 1 the size of our X bananas. But that's not going to extend to this. Remember from above that we had the vector outputs. So what we can do is we can fill in our vectors here. So apple is 1, 0, 0. Our bananas here, let's do it like this. These are going to be 0, 1, 0. And then we also have our grapes. So this would work just fine. And we can do that, and whoops, if I make my 0, 1, 0, 0, 1 for grapes. So now we have a 3000 element vector that has, 1, 0, 0 for is it an apple at the beginning, and 0, 0, 1 for is it a grape at the end, and somewhere in the middle we have 0, 1, 0s. So that's great. But of course there's a bit of efficiency here because you may have lots of categories, and you don't want to allocate hundreds of 100 element arrays or 1000 element arrays just to represent a single element that's hot. And so we call this a one-hot array, just because there's just one value that's non-zero. So Flux gives us a nice little helper function called a one-hot. And what it does is it's a function that takes two values. The first is saying which element is going to be the hot one, and the second input is the range of values that it could potentially take. So, you know, you might have a 300 different categories, right? And you want to say that the second one is hot. Or you might have 30,000 categories. It all depends on your machine learning task. You don't want to allocate a 30,000 element vector every time you want one of these things. So if you look at what one-hot is doing here, let's say it's you're selecting the second element out of 8 possible values, you can see it's only storing 2 values. It stores them as unsigned integers, so it's in the hexadecimal notation here, but you can see that it's the second value out of 8 possibilities is the hot one. And so, of course, you can have an arbitrarily large number of possibilities, and it's still just going to store 2 values. So that's a nice efficiency. So our y's can be defined in terms of one-hots instead of plain old Julia arrays. And these will work just like normal Julia arrays. They're booleans instead of ones and zeros, but it's essentially the same idea. So true, false, false at the beginning, and false, false, true at the end, with false, true, false somewhere tucked in there for the bananas in the middle. So those are our x's and our y's. Now, all we need to do is train our model. Now remember, this was the core algorithm from the previous lecture. It was a dense neuron with 2 inputs and 1 output. Well, we know that's going to be different, right? We have 3 outputs in this case. So let's uncomment this, and let's see if that works. So the only thing I've changed here from the last lecture, where we're doing a binary classification, was the number of outputs. I also changed the data, right? We needed to compress our data into the format that we needed. But the core algorithm here, the only change I made was in the definition of the model itself. And that trained our model with one run through the data. And we can visualize this now. It's a little trickier to visualize, right? Because we have 3 possibilities. We're asking 3 questions. Is it an apple, is it a banana, or is it a grape? So this visualization here, what it's going to do is it's going to draw a line that's the decision boundary between our apples and is it an apple, is it a grape? So here you can see we have 3 groups, 3 clusters of data, the apples, the bananas, and the grapes. And we have, we're supposed to have, anyways, 3 lines that are the decision boundaries between those groups of things. But our lines are so far off here that they're not even showing up. So the decision boundaries are somewhere around here and basically saying everything is all the same. There's no decision making going on, which we would expect, right? We've only trained this once. We need to do some more training. So let's go ahead and do that and implement our training loop here. Let's say 100 times train our model. So this will go through your data, do 100 loops of our training, and should improve the training. Now, while that's running, it's important to go back here and look at the data themselves. So recall, what we're plotting here is, on the x-axis is our mean red value, and on the y-axis is our mean blue value. And so the data, this is what our model is seeing. So all the best our model can do is draw lines between these clusters. And you can tell that it's not going to be able to do a very good job. They're pretty tightly overlapped here. And in fact, if you were to draw a straight line, you couldn't detangle our apples, which are in blue. The blue crosses here are the apples. You wouldn't be able to detangle these apples from the other things. There's no single straight line here that would be able to do that. So keep that in mind as we train our data. Still training. Give it 1 second and we should be able to, there we go. Now let's update our plot and see if we're doing any better. takes a second to plot because we're plotting all 3,000 elements of our data points. So it's a lot of data points. And there we go. Now we have our decision boundaries. And you can see that our decision boundary for is it a banana in green is nicely, has all the green on the one side and everything else on the other. That's a great decision boundary. Our decision boundary for is it an apple, that's also nicely selecting our apple. But, I'm sorry, that was our grapes. Our grapes are in red here. That's nicely selecting our grapes up top. But the apples, they're having a hard time, right? Our decision boundary is effectively this straight line that's trying to figure out how to go in there and grab out the apples, but it's not able to encapsulate that complexity that we see here. So this begins to give you the sense that we might need a slightly more complicated model to attack this problem. And we'll get to that in the next lecture. But I want to hammer home, so in this lecture we've talked about how you set up a machine learning task with multiple outputs, how you do a multiple classification problem with one hot vectors, and then the fact that when we did our training algorithm, the biggest work was actually in getting our data set up, in defining our labels, defining our known features, and loading all the data that we had. The model itself, the core algorithm, is just the same 4 lines that we had the last time. The only difference was how we set up our dense neuron. So that is multiple outputs, and it will set the stage for the next lecture on deep learning, where we begin chaining together multiple neurons so that way we can encapsulate more complexity in our data like this and hopefully be able to pull out those apples from the middle of the graph.